Okay, we'll start the class now. So in yesterday's class, we discussed about how to determine the stresses due to initial tightening. Then we discussed about how to find the stresses due to external forces also. So we are seeing some example problems also on stresses due to initial tightening. Those are, we'll call it as a internal stresses. Now we already discussed stresses due to external forces also. Due to external forces, we have two types of stresses. One is tensile stress, the other one is shear stress. So the tensile stress is calculated based on the tensile stress area, and tensile load divided by tensile stress area is going to be the magnitude of the tensile stress. And also suppose if you have a number of bolts which are taking the total external load, then you need to divide by total load divided by the number of bolts, then you will get the amount of external load per bolt. So while determining the size of the bolt, you need to compute what is the external load per bolt, and also you need to determine what is the internal load, that is the load due to initial tightening per bolt. So always you need to do the calculations per bolt, not for the combined all the number of bolts. So you need to keep this point in mind. So then okay, so this is the formula. And also suppose if you don't know have a standard data, so for this AT, so here we are already discussed, so how to get the tensile stress area from the data book, we are familiar with that. So now suppose if this data is not available, so that means, so how will you decide this AT, or how will you pick the AT value from the data book? If you know the nominal diameter of the bolt, then only you can pick it, or else if you don't know the nominal diameter, so you cannot take the data from the data book, because so always this tensile stress area is given against the nominal diameter. If you know the nominal diameter, you can pick the AT value from the data book. But in some cases you want to design the bolt, that means you need to determine what is the nominal diameter of the bolt. So in that case D is unknown for you. If D is unknown, so you cannot pick AT value from the data book. So then what you do is, in that case, but still the problem is needs D value, so then you need to use this relation, that is DC is equal to 0.84 D. Using this relation you can calculate the diameter also. So that means while calculating this AT value, you need to use this relation, DC is equal to 0.84 D. So with that relation you can find it. So anyway, so we have one problem, one such kind of problem we are going to discuss in this class. So we'll see that. So why you need to use this, or where you need to use this DC is equal to 0.84 D. Okay, so this is about the tensile stress. Then the shear stress. So this also we already discussed in the previous class, but only difference is in calculating the shear stress and in calculating the tensile stress is the area we are considering it for calculation of stress. Okay, so if you understand that, then it is going to be straightforward calculations only. So then you have a combined, that means if I have, okay, so here these are the formulas. So here while calculating the tensile stress, you need to use the core diameter, or DC plus DP plus DC by 2 you need to use to compute the tensile stress, whereas in case of shear stress you need to use major diameter of the bolt. So why you need to use the major diameter of the bolt is I already explained to you in the previous class. So using these formulas you can calculate the shear stress. If you want to compute the shear stress, you can use this, or if you want to calculate what is the shear loading capacity, you can use this formula. So both the formulas are same only, we are arranging in different ways. So that is the only difference here. Then you have a combination of both tension as well as shear stress. If you have combination, that means the bolt is subjected to tensile stress as well as shear stress, then now we can design the bolt. So in that case we need to use our failure theories. Since we are talking about only static loads here, so we need to use static failure theories to find the equivalent shear stress or equivalent normal stress. That is nothing but you need to find out what is the maximum shear stress and you need to find out what is the maximum principal stress. So that we know formulas from the failure theories, we are well aware of those formulas, how to compute maximum shear stress and also maximum principal stress if I know normal stress sigma and shear stress tau. So to compute that normal stress sigma t, this is the formula that just now we discussed. So this is the formula you need to use. If there are number of boards, you need to use this formula. Then for computation of shear stress, you need to use this formula. Once you have sigma t and tau, we can easily calculate the maximum normal stress as well as maximum shear stress. So this is the formula for the maximum shear stress, that is half into square root of sigma t square plus 4 tau square, and this is the formula for computation of your maximum principal stress, that is sigma 1. So which is nothing but sigma t by 2 plus half into square root of sigma t square plus 4 tau square. So once you have this, then you need to compare. So whether you are using maximum shear stress theory, if you want to use maximum shear stress theory, you need to equate this tau max to the your yield strength in shear. Of course, if you want to include the fatigue, sorry, not fatigue, it is factor of safety. Your allowable tau. Tau allowable is nothing but your shear strength in yield, SYS divided by FS is going to be the allowable shear stress. So you need to take this tau max and you need to equate that one to the allowable shear stress, which is nothing but your SYS divided by factor of safety. From that you can find the size of the bolt. Similarly, if you want to use maximum principal stress, then you need to compute the sigma 1. So you need to equate the sigma 1 to the allowable tensile stress. So then from that you can find the size of the bolt. So this is how you can analyze the bolt, or you can determine the size of the bolt when it is subjected to external load which induces both tensile as well as shear stresses. Okay, so now what we'll do is we'll take up some numerical problems on these external loads also. Then once we completed that, we'll move on to the combined both internal as well as external loads. So first we see only stresses due to the initial tightening. Those are nothing but only the internal stresses. Then this topic is stresses due to external loads. Then next category is when you have a both, that is load due to initial tightening plus external load is acting on the bolt, how we can analyze or how we can design the bolt. So for that, first we'll see stresses due to external forces. Then once we completed that, we will go to the combination of loads. So now this is the first numerical problem we are going to take up on these external loads. So just note it down. I'll give 2 minutes time to you. Just note it down and then we'll discuss the solution. So once it is completed, just inform me, just so that we can discuss the solution. Okay, so now you start note it down. Is it over?
Sir.
Okay. Right. So now we'll see the solution for this particular problem. So what he has given is an electrical motor weighing 10 kilonewtons is lifted by means of an eye bolt as shown in figure. So generally these eye bolts are used for lifting the loads. So here you use to lift the electric motor whose weight is 10 kilonewtons. So actually how it will work is, see here you can see the high bolt here in this figure, it has some threads here. So similarly a cylindrical hole with the helical grooves is drilled in this electrical motor, and then they will fit this bolt into that and they will tighten this. So then through this here they will place some kind of hook here. So with that hook it will pull up so that it can lift the load whatever attached to that through this joint here. So that is a general mechanism how this eye bolt can work to lift the loads. So here it is using for lifting a load of 10 kilonewtons. So by means okay, so the eye bolt is screwed into the frame of the motor. That's what I already told to you. So the bolt has 4 threads. So here he mentioned that the bolt has 4 threads. This is important point you need to remember. It is made of plain carbon steel 30C8. So which is having a yield strength of 400 Newton per mm square. And the factor of safety is 6 years given. To determine the size of the bolt, so here we need to find what is the nominal diameter of the bolt. We need to find what is the D value here. That's why he has given D as unknown here. So we need to find what is the size of the bolt. So for that only thing is, you know everything here. See, he has given the load on the bolt. So that is the tensile load. We'll consider only the tensile stress because you are lifting the bolt in the upward direction. You are using the bolt to lift the weight. So the weight is acting vertically downward here. So therefore the bolt is subjected to a tensile stress. So we'll ignore all other stresses, whatever may be, if they are minor in value, but still we can ignore that because we are using a factor of safety of 6 here. So we'll consider only tensile stress to determine the size of the bolt here. So we know the formula for tensile stress. What is the formula for tensile stress? Sigma T is nothing but load on the bolt divided by, here we are considering the external load, not initial load here. If it is initial load, you need to consider initial tightening, a load due to initial tightening. But here we are talking about only external load. We are ignoring that load due to initial tightening. So because he has not mentioned anything about that here in this particular problem. So we'll ignore that and we'll consider only the stress due to the external load. The external load is P, which is 10 kilonewtons divided by 80, that is tensile stress area. So in this, P is given to you, but sigma T is also given to you. So what is sigma T? Sigma T here is the allowable tensile stress. So he has given in the problem statement saying that this bolt is made of 30C8 plain carbon steel, which is having an ultimate yield strength of 400 Newton per mm square. So if no factor of safety used, then SYD is going to be your allowable stress. But here a factor of safety of 6 is used, so then your allowable stress, that sigma T, is nothing but your SYD divided by EFS, factor of safety. So that means you have given sigma T and he has given P. So then I can compute the AT now. So then once I know the AT value, so in the data book, from the AT value I can pick what is the nominal diameter also. So corresponding to, so if I solve this particular problem, so what I will get is, I can write the expression for AT is, I can take it as P by sigma T. So now I'll get some value for AT. So now in the data book, I need to choose coarse threads. I need to choose the coarse threads and I need to identify the diameter which is corresponding to this AT value, whatever we got it. So in that you need to choose a coarse series to find the diameter for the bolt. And also here, one more important point is, I think most of you people will make a mistake here. So conversion of the units. So load is in kilonewtons, stress is in Newton per mm square. So it is in newtons. So you need to convert this load is also into newtons. That is important thing you need to remember. So that's it. That is the solution. So now I'll show you the calculation part of this problem. So he has given P as 10 kilonewtons, Sy as 400 Newton per mm square, and Fs as 6. Then the permissible tensile stress is nothing but Syt by Fs, which is 400 by 6, which comes out as 66.67 MPa or Newton per mm square. Both are same. 1 MPa is equal to 1 Newton per mm square. So you can write it in MPa or you can write it as Newton per mm square also. Then the tensile stress area of the bolt is given by, just now I told you the formula, that is AT is nothing but P by sigma T. Earlier we used this formula as sigma T is equal to P by AT. Now I rearrange that so that I can get an expression for AT. So AT is nothing but P by sigma T. P is given as 10 kilonewtons. So therefore 10,000 divided by sigma T, just now we computed, which is 66.67. If you substitute that, we get area is 149.99 mm square. That means approximately 150 mm square. The area is, tensile stress area is 150 mm square. Now for a AT of 150 mm square, and we need to keep this point in mind. So we need to select coarse threads. So then, now if you open our data book, now you tell me what is the diameter we can choose for this application now. So
16, sir.
16, okay. Okay, right. So I'll come to that. I'll show you the data of the data book, and then you can see that also. Now, if you open the data book, so in the data book, that chapter number 8, you have a tables saying that in the table you have a basic diameter, a pitch diameter, that is table 8.7. If you open the table 8.7, in that our last column of the table is tensile stress area. So you can see it here. This is the last column, it is tensile stress area. You need to look it into this column first. So where your tensile stress area should be 150. That means you cannot take the area less than 150. So you have to take 150. Suppose if 150 is not available in the data, you need to choose the next highest number. That means 150 is not available, don't take it as 140 or 130, which is close to 150. Don't think like that. Always you need to choose the higher value while selecting the tensile stress area. So now, if I go back here, so the maximum values are here is in fractions only. So now, like next page, also the values are less than 150 only here. So then I'll move on to the next page, like that I'll go. If I go to M16, you can see that here, M16, I'll open like this. So now I think it is okay. So I need to keep it here only. So here for M16, I think you can see the value here. You can see the values here. So this is M16 for course series. So first value you need to take. Here the value is going to be 157. So now if I go for M14, here the value is only 115. I cannot select 115. So I have to select this one, that is M16. So the answer for the question is, you need to select M16 as the nominal diameter. So whatever column here you have, this value M16, this value, that is nothing but your nominal diameter. So like that, you need to choose the value from the data book. So I think now you can understand that. Is it visible to you here, 157? What I placed it here, I am pointing it to 157. Is it visible to you? Maybe if you have a data book, you can go through that if it is not visible. Okay, so like this, you can select the data and you can identify, you can choose the data from the data book, whatever you require. So now again, I am going to the presentation mode. So the solution is going to be M16. So assuming core series, because he has mentioned that in the problem, the nominal diameter D of bolt having minimum tensile stress area of 149.99 mm square is 16 mm. So from the data book. So this values comes from the data book only. So that's why I written here from data book. So then the standard size of the bolt is M16. This is the answer for the question. Right? So like this you can solve the problem whenever a bolt is subjected to the external load only. So here this problem is purely on only external load. We are not considered the initial tightening. Only purely external load. So then you can solve the problem using data book and the formula. Only one simple formula you need to use. With using that formula you can easily solve this particular problem. Okay? Right. So once you are done that, next we will move on to the stresses due to combined forces. That is, if you have a combination of load due to initial tightening as well as load due to external loads or external forces. So how you can find the stress due to these combined forces? So the resultant axial load on a bolt depends upon the following factors. So one is, the factors are the initial tension due to tightening of the bolt. Okay, so because your total load or resultant load is combination of these two, load due to initial tightening, which we will call it as initial tension. Then the second one is load due to external loads. So therefore, based on these two, you can calculate it. Not only these two, there is one more important factor which can be considered to find out the resultant load. That is the relative elastic yielding of the bolt and the connected members. That means, so we have not done this elastic analysis of bolted connection. Actually, that is important thing. Maybe in gate examination point of view, it is very important, but I don't know, unfortunately, which is not included in our syllabus. So we are not going to discuss that in detail. But only thing is, we'll discuss up to point what we require for our course. Okay. So the relative elastic yielding of the bolt and the connecting members. So that is, the springiness or the stiffness of the connecting members also will also influence the resultant load acting on the bolt. So because in our bolted connection, you are connecting two members through a bolt and nut connection. So whenever if external load is applied to this connection, the total external load is not taken by only the bolt only. So the connecting member will also take some amount of load. So therefore, whatever total external load is there, I cannot take the total external load as the load on the bolt. So you need to include or you need to consider only the fraction of that. So how I can decide that whether fraction of the total external load is taken by the bolt or nothing, or the bolt is not at all taking any load. So for that there are some factors here. See here you can see that different types of connections are there here. Here you have a soft gasket, here you have a rigid one. So in these two connections, based on this one and this one, so you can decide in which case the bolt will take the total load and which case the bolt will take no load. So here, when connected members are very yielding as compared with the bolt with soft gasket, like I shown in the first figure, then the resultant load on the bolt is approximately equal to the sum of the initial tension and external load. So that means here you are using a soft gasket, means so it is not capable of taking any load. So since it is a soft gasket, these things, so these connecting members are going to yield very easily. So that means they are not capable of taking any load. So therefore the total load on the bolt is going to be on the bolt only. So that means, so in that case you need to consider that to 100% of external load which is taken by the bolt itself. So that means the resultant load on the bolt is going to be the sum of the initial tension plus the external load. Whereas the other case, so the other case is the second one, that is you are using a hard gasket. On the other hand, the bolt is very yielding. So that means the bolt is weaker when compared to the connecting members. The first case is the connecting members are weaker when compared to the bolt will take the total load. So in the other hand, that means in the opposite to this, if the bolt is weak when compared to the connecting members, then the resultant load will be the neither initial tension or not the external load, or whichever may be the greater. In those two, whichever may be the greater, you need to consider only that. So but if you take any practical condition, you cannot compare or you cannot have a connecting members which are very weak compared to the bolt, or vice versa. You cannot have a bolt which is very much weak when compared to the connecting members also. That means you have a situation in between these two extreme conditions. So now if the situation, the actual situation is between these two extreme conditions, that means in one case the bolt is taking the total external load, in other case the bolt is not taking at all any external load. So the extreme, these two are the extremes, so zero load or maximum load. So now if you take a practical condition or actual condition, you have a in between of these two conditions. So therefore what you need to do is you need to consider a fraction of the external load which can be taken by the load, taken by the bolt. So that fraction we can find how much fraction the bolt can take. So out of the total external load can be decided by this elastic analysis of bolted connection. So anyway, we are not doing that analysis, but straight away we pick the value from the data book, how much fraction the external load is taken by the bolt. So for a given condition, that means depending upon the type of gasket you are using, so you can decide that. So in order to determine the resultant axle load on the bolt, the following equation is used. That is, the resultant load on the bolt is equal to PR, which is denoted by PR, which is equal to P1. P1 is nothing but the load due to initial tension. So that is because of tightening, whatever may be the initial tension is there in the bolt, that will take it as P1. We know that if it is a fluid tight joint, your P1 is 2840 times the nominal diameter D. 2840 times D is going to be P1 if the joint is fluid tight joint. If the joint is not fluid tight, so then in that case your P1 is nothing but half of that one, that is 1420D. So that we already know, P1 is already known to us. So in the external load, how much fraction it is taken by the bolt will be decided by this factor K. We call this factor as K, and this K will depend upon the type of gasket you are using for your application. So then I already shown you in that maybe the last before last class, this K value table is also there in the data book. So we simply what we need to do is we need to pick the K value from the data book for the given condition. So that if you refer to the table 8.2 or even this formula is also available. This PR is equal to P1 into K into P2. That formula is there. In the first formula itself, it is going to be that formula. So the K values are for K values report table 8.2 like that he has given in the data book itself. So if you refer the table 8.2, so in that he has given 5 different types of joints. One is metal to metal joint with through bolts. That is, in that case K may be vary from 0 to 0.1. Odd copper gasket with long through bolts, K value vary from 2.5 to 0.5. Soft copper gasket with long through bolts, which is going to be 0.5 to 0.75 K value. Soft packing with through bolts 0.75 to 1 K value, and the soft packing with studs is K value equal to 1. So these are the things you need to consider. So that means from the data book, from the table 8.2, you need to pick this value. So once you pick that value, we know the external load, we know the factor K, and we would also know the initial load due to initial tightening. So then I can calculate the resultant load. Once I have a resultant load, based on that I can compute the allowable stress. So from that allowable stress equation, I can find out the size of the bolt also. So right, so that is a general procedure when you have a combination of load due to initial tightening and the external load is there. So first you need to identify how much fraction of external load is taken by the load based on the factor K. This K can be selected from the data book. Okay, right, now we'll take up one more problem on this one. So it is also simple. Starting all these problems are very simple problems and also smaller problems in size. Simply we'll use only one equation, that is only the tensile stress. So maybe you may have a scope of getting only 2 marks or maybe maximum 4 marks in the examination. Okay, right. So now we note down this problem, then we'll discuss the solution for this also. So with this we'll complete this loads on the bolts, so which are subjected to direct load. So next we'll move on to the bolted connections which are subjected to eccentric loads. So that we'll see in the coming classes. Anyway, first you note down this problem, then we'll discuss the solution for this, and then we'll conclude for today. Then we in the next class, in coming classes, we'll discuss about the eccentric load analysis also. Okay, just note it down, then inform me. Once it is completed, we can discuss the solution. Okay, so I think it is over, right? Did you complete it? Note it down of this problem?
Yes, sir.
Okay, right. So now we'll see the solution for this. The cylinder head of a steam engine is subjected to a steam pressure of 0.7 Newton per mm square, and it is held in position by means of a 12 bolts. A soft copper gasket is used to make the joint leak proof. The effective diameter of the cylinder is 300 mm. Find the size of the bolts so that the stress in the bolts is not to exceed 100 MPa. So this problem is also similar to the previous problem what we discussed. In that problem also you have to find out what is the size of the bolt. Here also you have to find out what is the size of the bolt. So now, but only difference between this problem and previous problem is, in case of previous problem, you have only external load. In this problem, you have both internal load or initial load and external load also. How we can say that in this problem, the bolt is subjected to both combined loads or combination of loads. So for that, if you look at the problem statement here, the joint is he has used a soft gasket is used to make the joint leak proof. So whenever the joint is a leak proof joint, we need to consider the load due to initial tightening. So for a leak proof joint, we have the initial load or initial tensile load on the bolt is nothing but 2840 times D. 2840 times D. So that means that is the initial load is there, and because of this steam pressure, it is subjected to the bolted connection is subjected to the external load also. So that means, so first you need to compute what is the initial load, and then you need to compute what is the external load. So but remember here in this problem he has mentioned that there are 12 bolts in the connection. So in that cylinder head he has used 12 bolts. So now, like already told in the previous discussion, you need to calculate all the loads per bolt, not for all the bolts. So you need to calculate what is the external load per bolt and what is the internal load per bolt. Then from that you need to find out what is the resultant load. So once you have a resultant load, from that you can identify what is the diameter of the bolt. So that is the way of finding the solution for the problem. So now for this, he has given the first we need to find out what is the initial load. So initial load means straightforward, because the initial load is nothing but, since it is a giant is a fluid tight joint, your P1 is nothing but 4820.
Sir, 28.
Sorry, it is not 48, it is 2820. 2840. 2840 D, where D is the nominal diameter. But what happens here in the problem, he asked us calculate what is this D value. We don't know D value. So that means we know the expression for the initial load, but we don't know its actual magnitude. So still we don't know that, but still we'll keep that one in terms of this unknown D only, because we want to find this. Then to find out that this is the initial load. So this is the initial load per bolt only. This is not for all the bolts, it is per bolt only. So for each bolt, this is the initial load, you can say. Per bolt, this is the initial load, P1. Then external load is taken by the 12 bolts here. So the same cylinder head is made, in that he has used the 12 bolts to make the connection. So therefore, whatever may be the load which comes on the cylinder head because of the internal pressure, that load is taken by these 12 bolts. So therefore, here also, here you need to calculate for each bolt how much load is there. So that is the external load. External load, I will take it as P, which is nothing but okay. So P2, we can take it as external load, will denote it as P2. P2 is nothing but here the pressure is given it as 0.7 and the effective diameter of the cylinder head is 300 mm. So therefore, your P2 is nothing but 5/4 area, pressure multiplied by area, 5/4 D square, where D, capital D, you can use it here. Capital D is nothing but the effective diameter of the cylinder head. So 5/4 into 300 square is going to be the cylinder area multiplied by the pressure, which is 0.7. So this is
9.48 kilonewton, sir.
This is the load which comes under from the cylinder head on the 12 bolts, but we want to calculate it per bolt. So therefore, what you have to do is you need to divide this one by 12, so that you will get the load on the each bolt, external load on the each bolt, which is nothing but the total load due to this steam pressure divided by the number of bolts, which are 12. So once you get this one, then use your formula for PR. That is, the resultant load is nothing but P1 plus K times P2. The resultant load formula is PR is equal to P1 plus K P2. So P1 we calculated, but it is in terms of unknown nominal diameter D only. We'll keep like that only. So now we need to identify what is K value also. So for the K, what he mentioned it is a soft copper gasket is used for this application. So now, just now I read out all those values for K for different types. So again, he referred to table 8.2 in the data book. So in the table 8.2, for soft copper gasket with long through bolts. So here, since it is a cylinder head, we'll use through bolts here. So for that condition, for soft copper gasket with long through bolts, so the minimum value for K is 0.5 and the maximum value is 0.75. So you can choose any value between 0.5 to 0.75. So always we'll design for the maximum stress. So therefore we'll take the minimum value for 0.5. So therefore minimum value I'll take it as K as 0.5. So now I know everything. So I can calculate the stress in the bolt. So what is this resultant load? This resultant load I can express this one as the allowable tensile stress in the bolt multiplied by area of the tensile area of the board. So sigma T you can write it as, PR you can write it as sigma T into AT. If it is only initial tightening, that means this is not there. In that case also our formula for P1 is sigma T into AT. If you have only a complete external load is there, then in that case also the formula is sigma T into AT is equal to P2. Whenever resultant load is there, your PR is equal to sigma T into AT. So in that, sigma T is already given to you in the formula, that is in the problem data, that is 100 MPa. You can take this, but this AT is also unknown for me. So now if I take this equation, AT is unknown and even P1 is also unknown, but that is in terms of unknown D value. So that means two unknowns, one equation you cannot solve for this. So then what I'll do is, I'll try to find out what is this AT value in terms of this D. So that means, so like I already told, whenever you have a data is not available for you, you can calculate this AT based on your DC, that is core diameter 5/4 DC square. You can take it as 5/4 DC square. So again, we are taking a relation between this DC and D. What is the relation? That our DC is nothing but 0.8 times D. DC is 0.8 times D. So now in this equation, you have only one unknown, because we are able to convert this AT also in terms of this D. So one unknown is there in this equation, I can solve for the D value. So once I got that, I'll choose the standard value from the data book for that. Okay. So this is how we can proceed for finding the solution for this particular problem. Okay. Now I'll show you the calculation part of this problem. So anyway, these are the given, this is the given data, that is P is 0.7 Newton per mm square and number of bolts is 12. Effective diameter of the cylinder, it is 300 mm and the allowable tensile stress, actually it is will be capital T, 100 MPa. So that is sigma T is 100 MPa. So then first is computed the external load. So the total external force acting on the cylinder head, like I already said, it is 5/4 into D square into P, where D is the diameter of the cylinder and P is the internal steam pressure. So if you substitute D is equal to 300 and P is equal to 100, you will get 5/4 into 0.7 square into 300. It comes out as 49,490 newtons. So this is the total load on the 12 bolts. But we need to compute the load on for a single bolt. So therefore, external load on the cylinder head per bolt. Per bolt, it is going to be the P divided by N, which we take it as P2. That is 490 divided by 12, which comes out as 4,124 newtons. So this is the external load on the bolt. Then for a soft copper gasket with long through bolts, the minimum value of K is 0.5. So we'll choose the minimum value. Then, so you know the K value, you know the P2 value, and then the resultant axial load on the bolt, that is PR is nothing but your P1 plus K P2. So in that, your P1 is nothing but, since it is a fluid tight joint, you need to take P1 as 2840D, then plus K is 0.5 and P2 just now we computed it as 4124. If you substitute that, you will get it as 2840D plus 2062 newtons. So now we need to equate this one to sigma T into AT. So that's what I did. So also the load on the bolt, so you can write that PR, the resultant load on the bolt, is nothing but 5/4 into DC square into sigma T, wherever DC is nothing but again 0.8D, you can write it. So if I simplify this by substituting the value of sigma T, then you get it as 55.4 D square. Now you can equate these two, because this is resultant load and this is also an expression for the resultant load. If you equate these two, you will get a quadratic equation. So here it is a quadratic equation in D. So you can take 55.D square minus 2840D minus 2062 equal to 0. So that is a second order equation. You will get two roots for this. What you will get is, if you solve this equation, you will get two roots. So in those two roots, so one value is going to be the higher value. That means the solution for your quadratic equation is, or the form of quadratic root size, it is minus b plus or minus b square minus square root of b square minus 4ac by 2a. So you have there plus or minus symbol is there. So now here we have a question. So whether we have to consider the plus value, you have to consider the negative value. So if you take a negative value, it won't give you the solution. So always you need to consider plus sign only. So that means always you need to choose the largest diameter. If you take the lowest diameter, it is not going to solve your purpose, because okay, if you have a doubt, what you can do is you calculate the two values. That is you find out the two roots, so you'll get two values. Then you check back into this equation. You substitute that into this equation and try whether it is capable of withstanding that load or not. So like that also we can take that. So generally what we'll do is we'll take the plus value. So plus, that means the largest value you need to take it. So that is going, if you take the largest value, you'll get D is equal to 52 mm. So that means the size of the bolt is going to be M52. So the bolt of size M52 is used for this particular application. So now I think only no need to use the data book also for this, because so in this case straight away you have everything is there. Then only thing is you need to calculate those values and you need to find the solution for the problem directly straight away. So once you have a D value, then you can compare now. So with the D value, so you can counter check also whether it is satisfying the given conditions or not. So you pick the D value as 52 mm. So now for 52 mm, just you compute what is your tensile stress area. So you open your data book. In the data book, the tensile stress area for 52 M52 it is, if you use course series, it is going to be 1760. So now you substitute the data here, D is equal to 52, and compute what is the total load on the bolt. So then you do the reverse calculation. That is, you find out what is the tensile stress in the bolt. That is the total load. So the total load is nothing but 2840 into D. In place of D, you need to substitute for 52. So compute this total load. So you get that PR. And in the data book, you have a tensile stress area of 1760. So now you check this value and tell me what is the value of sigma T you are going to get. Then only you can say that your design is safe. D is equal to 52. So now you tell me what is this value first. What is the total load PR? What is the PR on the bolt for a bolt of M52? The initial tension we can calculate as 2840 into 52. So what is the total load? You tell me.
So resultant load 148 kilonewton, sir.
149 వస్తుంది కదా, 148 అంటే వచ్చింది నీకు?
అరే 148.7 sir, 148.7.
149.742 వస్తుంది. ఏమైనా 52 వేసావా? 2840 into 52 నేనా?
Yes sir.
ఎంత వచ్చిందమ్మా అది? 2840 into 52 147.680 ఉందనా?
Yes sir.
Then plus you have a external load, that is 2062. So then the resultant load is 149.742.
సార్ అంటే K ఉంది కదా సార్, K వాల్యూ 0.5 ఉంది కదా సార్.
అవునరా, సబ్స్టిట్యూట్ చేసినాకనే కదరా నీకు రిజల్టెంట్ లోడ్ ఫార్ములా ఏంటి ఇక్కడ ఫైనల్ గా సింప్లిఫై చేసిన తర్వాత ఏమొచ్చింది? 2840D plus 2062 కదా. యాక్చువల్ లోడ్ ఇస్ 4124. 4124 కి ఆల్రెడీ 0.5 అప్లై చేస్తేనే కదా నీకు 2062 వచ్చింది. సో దెన్ డివైడెడ్
అంటే K రెండోసారి కూడా యూజ్ చేసాం సార్. KP2 మళ్ళీ
రెండుసార్లు వేయకూడదు కదా, జాగ్రత్త సాగేయాలి. అంత డేటా ఉంది, సబ్స్టిట్యూట్ ఉంది, మళ్ళీ తప్పులు చేస్తే ఎట్లా నువ్వు?
ఓకే
రైట్, యూ క్యాలిక్యులేట్ నౌ స్ట్రెస్ వాల్యూ.
Sir, 85.1375 sir.
85.08 MPa. So which is less than 100 MPa. So that means your design is safe. Or else you do one more thing. So we are taking the D is the largest diameter. So now what is the other value for D if you solve this quadratic equation? You tell me the other value. One value is 52, the other value is, you tell me what is the value.
సాల్వ్ చేస్తే మైనస్ లో వచ్చింది సార్ అది.
Negative value వచ్చిందా? One is positive,
Yes,
other
sir.
one is negative.
ఎస్ సార్.
Okay, if it is negative, so no issue at all. So you don't have a negative diameter, complete. You can simply ignore that value, only take the positive value. So okay, so then in that case, only positive value is 52 means you will take this and we'll go proceed something like this. Okay, so once you've done that, after that, if you want, you can check that also whether your design is safe or not also. So still, you got some factor of safety here. Allowable stress is 100. 100 divided by some over 85, you get around 1.5 as a factor of safety. 100 divided by 85, 1.17 is going to be the factor of safety. So that means it's okay, it's fine. So you can say that your design is safe. Okay. So like this, you can solve the problems on these bolts when they are subjected to initial tightening, or when they are subjected to only external loads, or when they are subjected to the combination of initial load plus the external load. So now with this we completed this part. Then next we move on to the bolted connection, not only bolt here. So a bolted connection which is subjected to eccentric load. So this analysis is quite similar to what we did in case of riveted joints and also welded joints also. But in most of the case, it is most similar to the riveted joints, not welded joints. Our rivets are also having some diameter. Here we will take the bolt as also a only diameter, nominal diameter we will consider while designing the bolt. So whatever analysis we carried out in case of riveted joints, that is applicable here also. So that means already we know the procedure for how to find or how to do the analysis of bolted connection when it is subjected to eccentric load. But only thing here is there are three types of load, eccentric loads. One is the eccentric load is parallel to the bolt axis. Then the other case is the bolt eccentric load is perpendicular to the bolt axis. That may be the case, and it may have some inclination also. Or maybe the third case is the bolt eccentric load is in the plane of the bolts also. So like that you have different three different types of eccentric loads. So based on that you need to identify that what is the primary effect and what is the secondary effect. In case of riveted joints also we did the same thing. So when a bolt riveted connection which is subjected to eccentric load, so we have taken what is the primary effect, that is a direct shear stress, and then because of the eccentric load in the plane of the or in the which is perpendicular to the axis of the rivets, it will cause a secondary shear stress or torsal shear stress. Because of the torsal shear stress, we calculated as a secondary shear, and you have a primary shear stress, you have a secondary shear stress, and we try to find out what is the resultant shear stress from that. And then once you find the resultant shear stress, if you equate the resultant shear stress to the allowable shear stress, from that you get the size of the rivet in the riveted joints analysis. Here also we will do the same thing. So the only thing is the word rivet is replaced by the bolt. That is the only difference. As far as when the load is producing initial and primary and secondary shear in the bolt, so the analysis what we already done in case of the riveted joints is applicable here also. Similarly, in case of welded joints, we discussed two cases. That is, one is primary. There is a direct shear stress. That is first primary thing is there in both the cases of load cases, and in the other way is one case you have a twisting torsal shear stress, or in case other case you have a bending moment. So if the load is in the direction or in the plane of the joint, you have a twisting moment or torsal shear stress, that we call it as a secondary shear stress. Or else the other case, that is when the load is not in the plane of the welding, or it is perpendicular to the length of the weld. So in that case you have a bending moment. So because of bending moment you have a bending stress. So you have one shear stress and one bending stress. So now using these two values we try to find out what is the resultant shear stress using our maximum shear stress theory. Then we equate the shear stress to the allowable shear stress. We get the size of the weld in that case. The same procedure is applicable here in case of this bolted joints also. So that means what you do is whatever we already discussed, those concepts we'll use here also to find the solution for the eccentric loads. So anyway, we will see those things one by one in the coming classes. So today I'll stop at this point. So we'll continue these bolted connections or threaded connections in the coming classes for eccentric load analysis. Okay, right. So now I think I already posted the attendance in the classroom. So just respond to that attendance and you can leave the class. Yes, it is there. You respond it and you can leave the class. And also one more announcement is maybe tomorrow I am not going to take the class. I'll inform you. We will take my class tomorrow. So I think tomorrow we have a third hour. Maybe some other faculty will take the class. So I'll put the message in the classroom so that which class will be taken or who is going to be taken my class. I'll put that in the classroom itself. Okay, right. So today we'll close this at this point. Maybe we'll see in the coming classes.